Imagine a scattered list of numbers you need to order from lowest to highest. Doing this by hand, you'd scan the line for the absolute smallest number, pull it out, and stick it right at the front. That exact human instinct, finding the minimum and moving it to the front, is the core logic behind an algorithm called selection sort. To see how a computer handles this systematically, let's look at this row again. The computer creates an invisible wall to divide the numbers into two distinct zones, a sorted side on the left and an unsorted side on the right. Initially, the sorted side is completely empty, and the unsorted side holds every number. The algorithm repeats a cycle. A scanning indicator sweeps the unsorted side for the smallest value, moves it to the front, and expands the sorted zone to lock it in. The whole process is just about managing that boundary. The computer repeats that search for every single position until the unsorted side is completely empty. Now the second pass, the computer scans only the remaining numbers, identifying 12 as the next minimum. It swaps the 12 into the new front position, and the wall moves again. By the third pass, the unsorted pool is shrinking, but the computer still scans every single one. It locks onto the 22, swaps it with the 25, and slides the boundary over once more. This is the mechanical rhythm. For every position filled, we perform a fresh scan of everything left on the unsorted side. On the fourth pass, only two elements remain. 25 is the minimum, and since it's already at the front, nothing moves. The wall just shifts. The final remaining number is sorted by default, and the work is finished. The process is called selection sort because the defining step is that act of selecting the minimum value before any move is ever made. Now that we see how it works, we can measure how efficient it is. This is what computer scientists call time complexity, or basically, a measure of how the workload grows as the list gets longer. Selection sort has a significant flaw. It's totally blind. Because it's programmed to check every unsorted item to find the minimum, it performs a full scan on every pass, even if the numbers are already in the right order. Since the computer has to perform a full scan for every single item in the list, the work adds up fast. If you double the number of items, the computer actually has to do 4 times as much work. This relationship is what engineers call O(n)(. Because the work squares every time the list grows, selection sort becomes incredibly slow once you're dealing with thousands of data points. But speed isn't the only metric. We must also consider space complexity, which is how much extra memory a computer needs to do the job. Notice how the spheres swap places inside their existing slots. The computer doesn't need to create any new, temporary storage while it works. Because the memory needs stay the same whether you have 5 spheres or 5 million, we call this O(1) space. So we have an algorithm that is slow on time but incredibly light on memory. That trade-off is exactly why we still use it today. It's a perfect choice for tiny computer chips found in things like home appliances. In these systems, memory is very limited, and writing new data is physically taxing for the hardware. While it's not the tool for massive databases, mastering the logic of selection sort provides the essential foundation you need to understand how all computer algorithms manage the balance between time and space.